due to unexpected error, last lecture went off. So I continued the same semiconducting nanoparticles, nanomaterials further. Here, where last lecture we left at zero dimension, quantum dots, nanoparticles, one dimension, quantum wire, semiconductor. Usually, in all types of, whether it is metallic nanomaterial, nanoparticles, and semiconductor nanoparticles, or insulating, we get so quantum dots, quantum wire, and another one, the two-dimensional nanomaterial, that is the quantum wells. Quantum well. So the example for the quantum well is thin film. Okay, so that these are all in the form of nanoparticles, nanowire, and nanofilms. They give the novel properties compared to the bulk semiconductor. Bulk semiconductors. There are the number of properties as well as the applications. Let us take one by one. So properties and applications. Applications. So we know that we understood there are the indirect bandgap semiconductor, direct bandgap semiconductors. Okay, in case of the direct bandgap semiconductor, usually the indirect bandgap semiconductors are silicon and germanium, and the many 4 group semiconductors are indirect bandgap semiconductor. Normally silicon carbide, silicon is a 4th group, and also the carbon in the form of diamond is 4th group, so therefore 4th group, that is also indirect bandgap semiconductor. And in case of direct bandgap semiconductor, again there are two types. One is 3,5 and the one is 6,2,6. The both 3,5 and 2,6 are direct bandgap. So what is the specialty of direct bandgap semiconductor? Direct bandgap semiconductors are giving novel electronic properties, optoelectronic properties, optical properties, as well as the very good novel physical and chemical properties, photocatalytic properties. There are the various things are there. So let us take the one by one now. Okay, so here first one, let us take so that the electrical properties. So novel electrical properties. So electrical properties of the bulk semiconductor is due to the what is main due to the band gap of the semiconductor. In bulk, what happens? The band gap will not vary with respect to size. For different material, semiconducting material, band gap is different. But in case of when a particular material converted to nano, okay, especially in case of compound semiconductor like 3,5 and 2,6, the band gap is can be vary with respect to the size of nanomaterial. Band gap can be vary with respect to the added impurities. Okay, so that we know that the band gap can be vary with respect to size. Okay, so that size decreases. So this is the lowest and highest. So that the highest, it is lowest band gap. Okay, so that this is here higher and this is low and it is further low. So that electrical properties of the semiconductor also vary with respect to. This is the particle size is this is band gap. This is band gap. Okay, and this is size. This is lowest and this is highest. Okay, so that size of the material, for lowest material the particles, this is highest, and for highest particle it is low. Similarly, the electrical properties of the semiconductor also varies. Similarly, what happens in the one, the electrical properties also vary by the doping. For example, the transition element. Okay, transition elements like the, so conductors, some metallic atoms are doped. Then in case of some inorganic gases are doped. It's like that, when we dope some of the material, then the electrical property of the semiconductor will vary. So that gives the different novel electrical properties. Second one, another one, let us consider. So another one, because of this, due to this electrical properties, so novel electrical devices like this microprocessors, okay, electronic devices, and another one, the conducting polymers. This property is used in case of the conducting polymers. So that, and another one, the solar cells. Okay, solar cells or solar voltaics to increase the efficiency of the solar cell. It may helps. Okay, it is also used to produce the sensors. Okay, so that gives a novel electrical property and applications in various fields. Now let us consider another one application, that one optical, then another one property, optical property. So optical property we already studied, the optical properties of the semiconductor. Optical properties of the semiconductor is again depending upon the what band gap of the semiconductor. Okay, so that how the optical properties vary here. So that when usually normally in case of semiconductor, what happens, this is EC and this is EV. Okay, valence band, and in normally at the lowest temperature the valence band is full and conduction band is empty. When some energy is supplied to the valence band electron, they go to the conduction band and they come back to the original position that I mentioned now for the electromagnetic energy. So that here, so for that purpose, the semiconductors are, by the application of external energy means, so either you apply light or electrical potential. What is, so that potential, so what, then what happens, the electron go to the conduction band again, so that they come back to the original position by the emission of electromagnetic energy. So that, so in this way then it happens. Again, let us consider the lambda is the wavelength of the radiation. Then if the band gap has increased, what happens? If the band gap increase means energy gap increase, energy increase. For that purpose, when external energy is supplied to the electron, so that electron going to the conduction band while coming to the valence band, it gives the electromagnetic wavelength of higher energy. So that if the lambda 1 is wavelength here, lambda 2 is wavelength here, and lambda 1 is greater than lambda 2. If you write in terms of frequency, the nu 1 is less than nu 2. So that if you write the energy, nu1 is So greater than nu2. Lambda, smaller the wavelength, the smaller the frequency. This is less, correct. So the lambda 1 is less, nu1 is less than nu2, and E1 is less than E2, like this. So that, for example, in the same way, in case of semiconductor, what happens? So that when the semiconductor nanoparticle size, for example, consider gallium arsenide or cadmium tellur. Usually, normally in any website, it is usually you get lead sulfide nanoparticles. All these, if you observe, then so that the color bottles are there, the liquid filled with the color bottles. That liquid contains the semiconductor nanoparticle suspension. So that if the size of the nanoparticle decreases, the color will go on changes from red to blue. The highest the size nanoparticles having the least band gap, less band gap, the largest size nanoparticles. So then what happens? They are having the higher wavelength, largest wavelength, largest the nanoparticle size. They are having least energy. Similarly, when the nanoparticle size is increases, the band gap increases, and then what happens? This side is red and this side it is blue. Okay, as the size of the nanoparticles increases, band gap increases, and the color going from red to blue, red. So further it is higher band gap, red, orange, green, okay, then blue, like that. There are some nanoparticles, they work at ultraviolet, so that they absorb ultraviolet, okay, and so that they are transparent. So there are some nanomaterials called transparent TCOs, transparent conducting oxides. For example, zinc oxide and SnO2, okay, TiO2, okay, indium tin ITO, okay. So that the materials are called transparent conducting oxide. In this case, what happens? So normally, so all visible light are transparent, okay, they absorb only the ultraviolet. So for that purpose, these are all transparent. So this sort of the optical properties, so helps to produce the LEDs of LED and lasers of different wavelength or colors, different wavelength or colors, and again depending upon band gap. Okay, so that the next one, laser LEDs, and it is helpful in case of transfer, especially TCOs are helpful in what? Solar cells. Okay, so that like this, these are all some optical properties. And the next one, so they are useful in case of optoelectronic properties. Optoelectronic properties, what happens here? These are the optoelectronic devices, the devices which convert so light into light energy to electrical energy. And vice versa. So that these are all some properties that takes place. So that usually, for example, LDR, light dependent resistors. So that light dependent resistors, and again usually the flat panel displays, and and again we can take the lasers and LEDs. There what happens, electrical energy is converted into light energy, and light energy is converted into electrical energy in case of the light dependent resistor and some sensors. So that these are all the optoelectronic properties of the semiconductor. And again, what happens here, by with the changing in the size of the nanoparticles and the doping, okay, so normally in this case nanowires and the semiconductor films, okay, nanofilms, thin films are used to produce LDR sensors and the photovoltaics, etc., etc. These are the optoelectronic properties of nanomaterials. Next, let us nonlinear optical. Nonlinear. In case of nonlinear optical properties. So nonlinear optical properties means what? Here, so normally it is related to optical waveguides. What are optical waveguides? So that this is optical fibers. Optical fibers. So semiconductor nanoparticles or nanomaterials are very much useful in case of nonlinear optical. Nonlinear, why this nonlinear? Usually in the laser, usually in case of optical fiber, we know that it goes like this any places. So that optical fiber is laid somewhere. Then what happens? This is optical fiber. It is bent. Then if the light sent through this one, if the light is sent through this one, light can travel through this. Okay. So that this is reaches to out. Then why it is, how it is, although it is bent, we know that rectilinear propagation of light always travels in straight line. But what happens? It is bent. So it is working on the principle of total internal reflection. So that not simply totally. This is the property, the how much light reaches to the other end. So when light start moving in this or guiding through this one, so that it suffers number of losses. And finally, so that with the attenuation, large attenuation or loss, energy loss, it may reach. So that it is very important to minimize the energy loss when light is coming out. Otherwise, so that frequent upgradation of the signal required. So for that purpose, so we make many exercises. So that first the material, okay, ultra pure glass or plastic we are using, and so that to make the refractive index, to vary the refractive index as per the need, as per the quality of signal required, how much length we have to send the signal. Depending upon that, we dope some the semiconductor or dielectric nanoparticles to the host material, so that this is the performance of the optical fiber cable or the optical waveguides increases. The semiconductor nanoparticles are having the excellent the non-linear optical properties, especially those are transparent conducting oxides. Transparent conducting oxides used in case of non-linear optical properties, so that we get the effective sending of effective light signal or optical signal through the optical waveguides or optical fibers. These are some non-linear optical properties. So next, let us take Another one, and the magnetic semiconductor.